Hello, Matt Davis here with more homework quiz help. This one comes from section 10.2. In 2007, the M&M website stated that the color distribution for their candy varies depending on the type of M&M you buy. The color distribution claimed by the website for milk chocolate M&Ms is shown in the chart below. A current day stat student wants to conduct a test to see if the color distribution for milk chocolate M&Ms has changed since 2007. The student scooped 117 M&Ms out of a large bag of milk chocolate M&Ms, and the color counts for the student sample are also shown below. So we're going to make some changes here in the interest of giving help rather than answers. We're going to change our sample size from 117 to 119. And the way we're going to do that is by upping the color count for yellow from 13 to 14, and for blue we're going to change that from 14 to 15. And then what is it that they actually want us to do in this problem? If we look down at the bottom, they want us to calculate the value of the test stat, and they want us to calculate the p-value for the test. So let's go ahead and fill in this last column. I've kind of set up a table here. For our test statistic on this type, this is a chi-squared goodness of fit test. We want our test statistic to be the sum of the values of O minus E squared over E. So we're working at trying to fill in that column and get a total, and that will be our test stat. So the O in there stands for observed frequency. That's what we saw in our sample. So that's our color counts from the sample right here. And then the values of E are the counts we would expect if HO was true. And HO has always got that equal to idea to it. So HO is something along the lines of the color distribution is as claimed on the website, which would mean it goes by these percentages here. So when you calculate your expected frequency, you want to do n times pi, where pi is the probability or percentage that would apply if HO is true, which is going to be these percentages over here in this column. So that column right there represents the values of pi for us. When we calculate those, though, we do have to keep in mind that we need to multiply with the decimal form. So for example, this first one for brown we'll do over here on the side. So E for brown would be N, which is 119, times the value of P for that color, which is 13%, or 0.13. If we multiply that together on the calculator, we get 15.47. So that value is the one that would go right here, 15.47, and then we have 5 more of those to go. So we could just keep doing it like I just did there. So again, getting this number right here, doing this math over here. So we could just continue and do that 5 more times, but it's a little bit faster if we use the calculator to help us. So the way we typically do that is take the observed frequencies and put those in L1. We'll take these percentages in decimal form and put them in L2, and then we can build L3 ourselves by saying for L3 we want it to be N, which is 119, times the values of pi, which we're going to put in L2. So let's go to the calculator and see what that looks like. So I already set this up a little bit, so I'm going to go into the stat menu and choose edit. And you can see I've already put the observed frequencies into L1 and the decimal form of the percentages in L2. So now if I use my up arrow to highlight the L3 list, so I'm moving from L11 to the top so that L3 is highlighted. And now below the chart it says L3 equals, and I can type that expression, which is 119 times the values in L2. And the L2 button is right above the 2 key, so second L2. So when I do that, notice for the first one, I get that 15.47 that we just wrote down, and then I also get the other 5. So let's go ahead and move back over and fill those in the chart. You could do them one by one, but there's definite advantage to trying to use the calculator to do it all, and that advantage will come through more as we keep going on the problem. All right, so we got the 15.47 already. Writing down the rest of them, we have 16.66. 15.47, 28.56, 23.80, and 19.04. One of the things that's handy to do is to check the total on this and make sure it comes up to the same 119. that you had on your list. So one way we can check that real quick is go back over to the calculator. We can do this from the home screen. If we hit the list button, which is above the stat key, so second and then list, we can choose the math option on the far right and get a sum, which is the fifth option there, and then tell it we want the sum of that new column we just made, which is L3. And if we did it right, the total should be 119. And there it is. So that's a nice check on your work. So going back over there, we can fill that in, 119. So now we want to start doing our test statistic. So we can fill in the first one, the one for Brown, by doing the O minus E squared over E. So let's do that work over here on the side. Our O was 24 for the first row, minus the E, which is 15.47. We would square that and divide by E, which is 15.47. So let's go to the calculator and give that a quick try. So open parentheses, put the O in there, which is the 24, minus the E, 15.47. Close the parenthesis and square, that way you're squaring the result of the subtraction, and then divide that by E, which is 15.47. And this is like a z-score for that row, so we refer to that as a mini z-score. Our rule for rounding z-scores is 3 decimals, so we'll follow that here and go with 4.703. So let's go back and write that down. So 4.703. So just like we talked about before, we can now repeat that process. So this value right here came from doing this work right there, and we could repeat that 5 more times to get 5 more values. But the other option, that's a better one for us, is to go to the calculator and do all of them at once. So if I go back into Stat and Edit, I can arrow over to L4 and do open parentheses, and I want to do O, but the values of O are in L1, so second L1, minus E, but the values of E are in L3, so second L3. Close the parentheses and square, and then divide by E, and those values are in L3. So if I do that, I get the 4.703 that we had a minute ago, but I also get the other 5 values as well. One thing to be careful with, I know that when I do this on the actual TI-84, I saw 1.3265 for this highlighted number, which if you rounded to 3 decimals, you'd put 1.3267. Instead of looking where it's highlighted, look down below the table and they put more decimal places there. When you're rounding, always look at the one that has more decimals, otherwise you can have the problem of rounding twice and getting extra rounding error. So anyway, we're going to round all of those to 3 decimal places and put them into our table that we're making. So let's head back there. So we have 0.425 and then 1.326. This is the one that if you don't round using the bottom on your TI-84, you can get a mistake on. And then 6.438. and 0.329 and 1.866. And then we want a total for those, and that total will be our test statistic. So we could just type those 6 numbers back into the calculator with addition in between them and get it that way. But we could also use the calculator to get the sum of this list, and we did make this list L4. L4 we made L1 minus L3 squared over L3. That gave us those numbers, and now we can take the sum of that to get our total. So going back over the calculator, exiting out to the home screen, hitting the list button, which is above stat, so second list. Last column over is math. 5th item down is sum. We want the sum of the stuff that is in L4. So totaling that up with 3 decimals, we get 15.087, but that first 7 is followed by another 7, bigger than a 5, so we'd round up 15.088. Let's go back and write that down. Sorry, I guess red is fine, but we'll switch back to the blue. So 15.088, and that is our test statistic. And notice they did ask us to round that to 3 decimal places. And that's what I did. I did that the whole way through. You will sometimes get a different total if you add the actual rounded numbers, but it's more accurate to round the unrounded ones in the calculator so that you don't get as much rounding error buildup. And in fact, if you kind of look at the last digits, you can see 3 plus 5 is 8, plus 6 is 14, plus 8 is 22, plus 9 is 31, plus the 6 would be 37. So if you add those last digits, it ends in a 7, and we got an 8. So you can see you do get a slightly different total if you add the numbers that are written down in the individual rows instead of using the ones in the calculator. I'll take either one, but the ones in the calculator are a little bit more accurate. So anyway, there we are halfway through. We've got our test stat, and really we're a lot more than halfway through. The p-value is a much quicker step. So for our p-value, we want to look at an area under a chi-squared curve. Chi-squared curves start at 0 and then they're right skewed. Chi-squared curves have a df, and in this case the df is equal to 1 less than the number of row categories we had. We had 1, 2, 3, 4, 5, 6 row categories there, so we're going to have 6 minus 1 or 5 for our df. If you drop down from the peak and a little bit to the right, that's where the df would be. And then our test statistic, 15.08, this is 0 here. So if that's 0 and 5, 15.08 would actually be off the picture. So I'm just going to put it right here, but it would in reality be even further to the right, which means that this area we're trying to find over here for our p-value is actually going to be smaller than it appears in the picture. And how do I know it's that area I want? Because all chi-squared goodness of fit tests are right-tailed tests. So that's going to be right-tailed every time we do one of these guys. So that will be our p-value. And that's going to be equal to the chi-squared CDF of our test statistic to infinity with 5 degrees of freedom. So we can go get that from the calculator, and I'll do that real quick, and then we'll be done with this guy. So let's see, we want to go into the distribution menu. It's a common mistake for people to use row 6, which is TCDF, because you're so used to that from the last chapter, but this one's a chi-squared, so do chi-squared CDF. Our lower bound, or left bound, is our test stat, 15.088. We're going to go forever to the right, so our right boundary is infinity, so alpha I, and then number of degrees of freedom is 5. And we expect a small answer because it's just a little bit of area out in the tail. And when I press enter, I get 0.0099. But that 99 is followed by a 9, so we're going to round up, which can be tricky. Think of it as right now we have 0.0099, so we're going to round that 99 up to 100 and have 0.0100. So switching back over, we have 0.0100. So that's our p-value, which they wanted us to round to 4 decimal places. It is a probability, so that should be fairly natural for us to do that. So there's our two answers. We have our test statistic to 3 decimals. We have our p-value to 4. Some places that this can go wrong, make sure you remember to convert your percentages in the chart to decimal form when you do your multiplication or when you put them in the calculator, whichever way you do that. Sometimes people accidentally multiply by these values of O right here instead of multiplying by N, but every one of our percentages actually should be getting multiplied by the 119, not the individual values of O. Sometimes people will divide by O, but it really is supposed to be E that we're dividing by, so you need to be careful with that. Making the mistake of using TCDF instead of chi-squared CDF is common because we're used to using TCDF when there's a DF, but now we have a new curve that also has that DF. And then sometimes, I don't know if this is a real common mistake or not, but they want to see if the distribution has changed since 2007. So back in earlier chapters, we would hear words like changed and say that doesn't have direction, so it's two-tailed. But all of these chi-squared goodness of fit tests are right-tailed. So even though it may sound two-tailed, it's going to be the area in the right. And we're not going to double because it's not two-tailed. So those are some things to be careful with. Hopefully somewhere in there you saw what tripped you up, and good luck to you as you head back to the test.